back, everyone, to our final talk of the day and the final talk of the Cox Room in PyData. Today we have two speakers, Tony Bagnall and Chris Holder. Tony has been working as a professor of computer science, first at the University of East Anglia, where he was supervising the PhD student Chris Holder, and now more recently he's moved to the University of Southampton. Together they have also worked on the package aeon, which they will be discussing today for time series. So let's give all a warm welcome to Tony and Chris. The floor is yours.
Brilliant, thank you.
Good morning, thank you. Ooh, bit echoey. Okay, so we're here today to talk to you about some work we've been doing with distance functions for time series. Now, this is all part of the aeon package. Aeon, not eon, big debate about that. And this package is an open source Python toolkit, scikit-learn compatible, that grew out of a project with the Alan Turing Institute and is now funded by the UK government through the EPSRC scheme in order to promote research in time series for science. Now, the ethos behind aeon is to try and reduce the time it takes between people like me coming up with ideas for how to do time series machine learning and people who are practitioners using it, right? We want to reduce that pipeline. You know, you read a paper, we write papers, we try and look really clever, we put in loads of maths, you think that seems like a great idea, but how do you use it, right? We want to shorten that development time from coming up with an idea to people being able to utilize it. Now, my normal crowd is either undergraduates or academics, right? So it's the first time I've talked at a PyData event, so I'm not quite sure how to pitch it. So if I get it wrong, do let me know and feedback for next time. I'm going to start off just giving some motivation and background into time series machine learning. This is my research field, so I'm going to give a very high-level overview of the types of problem we address in time series machine learning and the types of data sets we use to evaluate our algorithms. We'll end up with motivating why we need distance functions and why we need time series specific distance functions. So I'm going to describe some of these functions and how they actually operate algorithmically before Chris steps in and introduces his implementations, which is part of his PhD, which will describe how we actually use them with data. Finally, if there's time, we'll talk a little bit about a paper we just had published, Chris is lead author on, using distance functions for clustering, time series clustering. So very basic, what do we mean by a time series? Or what do I mean in terms of my research by a time series? Key points about a time series for us are they're ordered. Now, the ordering usually is in time, but it doesn't need to be. The specific characteristic that makes it a time series is the ordering is important. Right? So you can't re-index all your time series and still use the same algorithm and still learn the same things from your data. We focus specifically on real-valued time series. Okay, so obviously you can have categorical time series, but my research focuses purely on real-valued series. And these occur in all areas of science and business, right? Just in terms of terminology, we say if we have a single variable observed in an ordered way over time here, such as GDP, we call this a univariate. And if we have multiple time series that are aligned, such as here we have an EEG scan, we call that a multivariate problem, and we refer to each time series as a channel. Just so we're clear about what we're talking about. Right, time series machine learning. Most people, when they think about time series analysis, they think about forecasting. Right? Forecasting is a huge field. There's massive econometrics and everyone's business is driven by forecasting, and there's a whole host of algorithms around it, many of which have developed from statistics. Now everyone's throwing deep learning at it, etc., etc. This isn't my primary area of interest. What I'm interested in is more general machine learning. So the classical machine learning problems of clustering, classification, and regression all occur in time series. I'll give you a few examples of these in the subsequent slides. But if we have a collection of time series and a label, then we may want to build a machine learning model on it, right? A predictive model that predicts something that isn't just the future values of the series. You also have time series specific problems, things like anomaly detection in time series, right? It's very different to anomaly detection in tabular data. Query by content rule discovery and motif discovery. But my main research theme is coming up, and what my group do, we come up with algorithms for clustering, classification, and regression that are specific to time series. Because if you just use standard off-the-shelf machine learning algorithms, they do not perform as well because they do not allow for the time-dependent data. So when we come up with these algorithms, right, what we do is think of a clever way of doing something under some use case, and then we evaluate it. Right? And in machine learning, generally, we like using real-world problems to evaluate our data set on. So some of the problems we use are part of a repository of data sets. You know, you've got UCI has a standard repository for machine learning. UCR, University of California, Riverside, hosts some generic data sets which are used for time series classification and the evaluation of algorithms. Right, so when we get to the end, I'm going to compare some different algorithms, and when we do that, we evaluate them on this very diverse, wide range of data sets. I host them on the website timeseriesclassification.com in collaboration with Riverside, and the regression problems we also host, and that's in collaboration with Monash. So this has been ongoing development, right? Eamon first proposed it in 2002. We've expanded it. We've donated problems for data sets which we've obtained from scientific collaborations, basically. So we work with people, time series are everywhere, we work with people in spectrograms, and with medical. When they have a data, if they can release it as an open source data set, we put it in a repository and people use them to evaluate their algorithms. Just a quick, brief overview of the types of data we host and the types of problems. I'm particularly interested in EEG at the moment. So EEG data, you wire people's heads up, you record the electrical activity. There's a host of machine learning issues, problems that derive from EEG. One of which we're looking at is the detection of early onset dementia. Right? So we're working with people in Cambridge. They want a low-cost machine learning-based algorithm for running an EEG on someone and seeing if they may be at early risk of dementia, because the earlier you treat it, the better the outcomes. EEG is also used in BCI, right? Can I detect whether someone's moving their arm or even thinking about moving their arm? It's also used a lot in psychology. But the key point is they get a whole bunch of these data. We've got labels. How do we build a predictive model given this sort of data set? It's everywhere. Time series data is everywhere. I cannot talk to anyone in any area of science or even business, and they've all got time series. Most people don't use bespoke techniques for them. They just kind of do some general data engineering, which is they think would be a good idea, and they don't follow a good scientific method for evaluating techniques. So all sorts of sensors, and human activity recognition is another area we're interested in. Everyone's wired up, right? You detect people's motion in the XYZ and also acceleration. What can you do with that data? There's a whole host of applications such as detecting if people fall over in the home, all the old Internet of Things stuff. There's loads of research groups around the country, around the world really, who are researching algorithms that build predictive models of this type of data. Now, at the heart of any system that uses time series in machine learning, you very often want to measure the similarity between series. Okay, I've got two time series. A fundamental question is, how alike are they? Now, in your simplest use case model, you could use a classifier, right? You could use a one nearest neighbor classifier. Here's a time series. I find the closest one in my data set, and I use that label as my prediction. But you measure distance between time series all the time, right? So fundamental in a whole host of algorithms is this thing of I've got one time series, how similar is it to another? And the question we're talking about today is how do we measure that? If you give me two time series, I want to quantify how similar they are. Now, similarity is subjective, right? So at the heart of it, the essence of saying this thing is like that one kind of defines what you mean by to be like it, right? When we see it, sometimes it's obvious. Okay, I can say these two things are very alike. They've got the same shirt, same trousers, they look kind of the same, right? So most people would agree that if I'm going to quantify the similarity between these two objects, I would have high similarity or small distance, right? The distance between them is small. However, Sometimes it's more difficult, right? So if I give you these two images, you can say, are they alike? Well, on one level, they are very alike, right? The similarity is high. However, on a fundamental level, they are not alike, right? So and this relates to time series as well. What do we mean for two time series to be similar? And when we talk about elastic distances, this is crucially what we're going to compensate for, is how standard similarity falls down when we think things are quite similar. Now, measuring similarity basically comes down to, excuse me, a distance function, right? The fundamental operation is I have two time series and I want to measure how far apart they are. Simplest distance function is Euclidean distance, right? We just measure the distance between the points, square them and add them up, and take square root, and that gives us a standard distance function everyone's probably familiar with. There are many other standard distance functions available in SciPy and all these packages. We could generalize it to the Minkowski distance. We could talk about Manhattan distance or correlation. The key point about all these distance functions is that you could re-index your two series and they would be the same, right? There's no shape characteristic in this data, in this measurement. If we look here, we're going to say that these two time series are quite similar because they've both got a hump. Now, if I re-indexed it and I put the peak of one at the beginning, the other at the end, Euclidean distance would be the same. And what we want to do with an elastic distance is compensate for that, to actually come up with a measure that says, well, these are quite alike, but they're slightly off an index. So just to motivate that a bit more, why do we need an elastic distance? So here's three time series. Series 1 and 2 are with the peaks, and series 3 is the one through the middle. Now, intuitively, on my notion of similarity, I would say series 1 is more like series 2, the two peaks ones, than is series 3. But if I measure Euclidean distance of these two time series, we find that the distance between 1 and 2 is greater than the distance between 1 and 3. What an elastic distance measure does is realigns them. So it compensates for that so that our similarity between 1 and 2 is greater. That is, our distance is smaller than it is between 1 and 3 and 2 and 3. Right, so as always, I'm going to speed this up a bit. If we look at the pointwise distance between series, so now I'm just going to motivate how dynamic time warping works, right? This algorithm. So if we look at the pointwise distance, we see by going through the indexes along the diagonal, we reach these big two distances, which is the distance between this point here and this point here. What if we could realign it? What if instead of going down the diagonal, we could just shift and move 0.4 onto 0.5? And that's essentially what elastic distances do, is they realign the series so that our measure allows for this small out-of-phase index. So this is the algorithm for DTW. Essentially, we generate this cost matrix, and then the final distance at the end is our dynamic time warping distance. It's a dynamic programming formulation, but it's really quite simple. All we do is each point is we look for the minimum around there, and then we add in the pointwise distance. And what this does, just a bit of code here, Chris will show a bit more, is essentially it shifts the index of these points to align them better. And now we see that if we have the distance between 1 and 3 is greater than, on the previous example I showed you, than the distance between these two. Okay, that's the essence of what's going on. It's allowing compensating for small phase misalignments by shifting the indexes. It's wildly popular. The only example I've got on here is from another core developer at Aeon, works for Halion, who make toothpaste, and he sent a link to this the other day, so I put it up there. But you will see dynamic time warping as a fundamental operation used very widely. It came out of speech research 50 years ago, right? It became less popular in speech, but it is still considered the standard way of measuring distance between time series if you're going to have some misalignment. There is, however, a host of alternative approaches based on edit distance. This idea of warping, moving the index to one to the other, there's another theme of research that looks at editing, that is, removing a series to form a combined one. Now, this is pretty standard if you're looking at discrete series, particularly DNA and things like this. Edit distance is just how do you transform from one to another? And there's a whole bunch of research that's described how you could adapt this massive body of literature towards real-valued time series. So what edit distances do is that rather than say, well, let's warp it onto one, they do the similar operations, but say, well, what if we delete it or insert it? Now, I've not got time to go through in great detail about how these algorithms work, but I should just do one very quickly analogy from one to the other and introduce one algorithm which we found to be most effective. Essentially, what you're doing is you're rephrasing the problem of DTW, this diagonal moving up or down, as having a match, which is move on diagonal, an insert, which is move on one axis, delete is move in the other. And you have a cost associated with each of these operations. So just as when you edit distance a word, if you change a letter, right, that has a cost associated with it. This is a similar thing we're doing with elastic distances. Okay, I'm just going to talk about move, split, merge. So essentially, this algorithm was proposed about 10 years ago, not by us, it's someone else. And what this does is it replaces that pointwise measure, the m there is the pointwise distance between I and j, with the cost function. Okay. Now, again, the slides will be available. I've got an example of how it works. But essentially what it does, rather than just use the pointwise distance when it's doing the warping, it looks at the 3 series and sees what would happen if we removed that peak. So the cost associated with MSM is all about what if I took that data point out of the calculation, or indeed put one into the other one? Okay, so I always talk on too much, but I shall now hand over to Chris, who will describe some of the distance functions that are available in Aeon.
Yeah, so we've just seen the theory for elastic distances and edit distances, and they're pretty complicated at times. So what we've tried to do in Aeon is make it really simple for you to use and understand them. And we've done that through both optimizing our documentation and making our API compatible with other languages such as scikit-learn, so they seem very familiar to you. So our documentation, our API, is on aeontoolkit.org, and we spend a lot of time working on this, and there's some really good examples on there if you want details in the future. But we offer a wide range of elastic distances and regular distances in Aeon, all of which can be used in the same way. So we support, for all of them, we support univariate, multivariate, and unequal length. When we say unequal length, it's when you have 2 time series, which one may have a recording that lasts a day longer than the previous one, which is quite common in the real world, that your time series will not be the same length. So we've put a real priority on making it work for unequal length. We've also optimized them using number, so they can perform, especially on the cloud, and so your server bills don't go through the roof. So we have gone with a very simple API. You would, if you've used either SciPy or scikit-learn distances, we follow the exact same format. You can either import our distances directly, so DTW distance, or you can use a utility function and specify your 2 time series and then a metric string. So in this instance, we have DTW. So your time series are just x and y, and you get a single floating point number, which is the distance between the 2 time series, which uses the elastic distances. You can also have parameters for a lot of these, and I'm not going to go into all of them today, but they're all on our documentation. A warping window is a common one to restrict how far the elastic distance can warp. And you can just specify these by passing a keyword argument of window to it. And again, this is all documented in great detail on our API. But we also have alignment path in API. We've decided to open this up as well. Normally this is kept closed, so in TS-Learn it's quite hard to get the alignment paths if you need them for other things such as averaging. So we've also have our API open for the alignment paths, and you can use all the elastic distances to get their alignment paths, and again, they all work for unequal length and multivariate. And you can use them in the exact same way where we can import it directly, so this is MSN, or we can use the utility function. And in this instance, you get 2 return values. The first value is your alignment path, and your second value is the distance in case you need it. And all that shows is a list of tuples where it shows which point in the first time series warps to the second point in the second time series. So then you can use other functions. Sorry, this is just with parameters. you can use our other functions in the library to plot your alignment path so you can see exactly where your time series are warping for your use case, which is really important if you want to use this, is you want to go, okay, does it make sense that my warping path is warping? Is it too free? Is it warping all over the place? Maybe then I should add a window parameter to it to stop it going all over the place. So finally, as our API, we also have pairwise distance functions. Now, this is when you have a collection or a data set of time series, and you want to say, okay, I want to measure the distance between every single value in my data set between every other value, so that you know the distance between them. And this is really common. And we support all of these, all of our elastic distances and our non-elastic distances. We don't have support for unequal length for this yet. But we're hoping to get this in the new version of Aeon coming soon. So again, this time we specify a data set, so there's just 3 time series in this data set, and we say what's the TWE, pairwise distance, and we get a matrix back, which is every combination of distance. Now, if you are doing more than one distance computation at once, you're going to want to use these pairwise distances because they've been optimized for doing it over data sets. So you can do it between one data set, or you can specify 2 data sets and say, what is the distance between these data sets? And you get a similar result. You can also use the parameters as normal by specifying keyword argument. And you can use them with scikit-learn, which I think is quite important, and your other models. So a common way you would do that is you have a pre-computed argument, and this is where you provide a pre-computed pairwise. So in this instance, we pre-compute our pairwise distance matrix, and we pass it to the fit of our SVM model here. And we pass it to our score, or I guess your predict, and you can use these with scikit-learn models as well. You can also directly pass the pairwise function instead of doing a pre-computed. So here we pass the MSM pairwise function as the kernel, and that just makes your code a bit more concise and cleaner, and it should all work with scikit-learn and other libraries. So you can also use it, this is just another example with clustering module as well to show that it works across modules. This is pre-computed again, just pass our pairwise matrix to fit, and then we get our labels out. And you can make it more concise again by just passing in directly the pairwise matrix. So that's just a code example. So I'm going to pass back to Tony just to finish up.
So just to wrap up, I'm just going to introduce this paper which was published this month. Chris is part of Chris's PhD, and really just to address why do we need these other distance functions? What's the point? If we've got DTW, why do we need other elastic distance functions? So Chris implemented them all. We ran them all on those archive data sets I mentioned before. So we got 112. We do 30 resample. Maybe we didn't on this. Anyway, we run them all, and we compare basic classification algorithms using this distance function. So most people, remember, use DTW. We found that DTW was significantly worse at clustering than Euclidean distance. Right? This surprised us because everyone uses it, right? But MSN and another algorithm called TWE was significantly better. There are reasons for this, gone into great depth in the paper, which I encourage you to read. But it shows that they are finding different things. Now, there's a rationale for doing this. This is with k-means clustering, which is a very standard form of clustering. We also looked at k-medoids and various differences. But the take-home message from this comparative analysis was actually, if we're clustering time series with a distance function, with standard clustering algorithms, you are better off using one of the edit distance-based ones, like move, split, merge, than dynamic time warping. Now, it's not to say dynamic time warping isn't hugely useful and brilliant and fantastic. It took us a year and a half to get this published because the reviewers thought it was brilliant and fantastic and how could it be better? But what we're saying is there are use cases for different distances. Okay, I'm not talking about Barry center averaging because that's a whole talk in itself. Okay, I think that's about my time. All I'll say is Aeon is an open source project. We do have a full-time developer funded by the government and myself working on it. We're very keen on collaborations. Part of the reason for coming here, we focus most on science and academics, but we want to broaden it out, and we would welcome everyone's contribution. Distance function is quite a good way of doing that. A whole host of other distance functions and distance function-based algorithms. So if you want to get involved, please get in touch. Okay, thank you.